So this talk basically discuss how to distinguish cosmological models. Cosmological models, I mean mainly early universe models like inflation or bouncing scenarios. More specifically, I will discuss about how to distinguish single and multi-field models of inflationary scenarios using some quantumness of primordial perturbations. So this is what I am going to discuss. So this talk is mainly based on a work recently put it in archive with Sumando Chakravarti. So let me start. Okay, so actually what we observe, okay, we have this CMB anisotropy map. So we observe this difference in the temperature that we all know that. So what we calculate temperature or difference in temperature and take the correlation function. I mean, calculate the difference in the temperature in different directions and take the correlation functions and average it. That is what we observe and calculate. Right? So this is the temperature correlation function. We can get this information from CMB. Okay. So from this data or information, if we assume lambda CDM and also GR, you can reconstruct back the primordial power spectrum. Okay, so I will discuss what is this primordial power spectrum. From this temperature correlation functions, you can construct back primordial curvature perturbation. This is a perturbation in the curvature in the space. Okay, so you know that this temperature correlation function can be mapped to perturbations in the curvature using GR, right? So using that, you can reconstruct back the primordial curvature perturbation. So this power spectrum, power spectrum looks like this. This is nearly scale invariant, and the amplitude is almost 10 to the minus 9. Okay, those are the main information we get from the power spectrum. Okay, so the interesting fact is that this power spectrum can be obtained from different models. There are lots of models, even single and multi-field models. But for my purpose, I just categorize into two categories. One is single field models. There are different single field models and multi-field models. So the question is, given the power spectrum can be obtained from these models. How to distinguish these models, single and multi-field models? That is the question I'm asking here. So what is actually this power spectrum or these primordial perturbations? So as you already know, these fluctuations are actually, these perturbations are actually quantum fluctuations originated during inflation. Okay, so this is the fluctuations in the scalar field, and also this fluctuations in the scalar field induce fluctuations in the space, and combine these two, these fluctuations in the scalar field and the fluctuations in the space can lead to anisotropies in the CMB. So that is the current scenario of the production of anisotropies in the CMB. Okay. So what I mean is these fluctuations are quantum fluctuations. Okay. That is originated during inflation. And if you model these fluctuations or model the inflationary scenario, you will see that the Hamiltonian associated with these perturbations is simply a Hamiltonian of time-dependent harmonic oscillator. And these primordial perturbations are usually characterized by a variable called Mugano-Sasaki variable. So this is the Hamiltonian we get when you model an inflationary scenario with single field. Okay, so how do we quantize and how do we calculate this power spectrum? As I said, these are quantum fluctuations, so we have to calculate the power spectrum. I mean the quantum correlation functions, which is the power spectrum. So just take this Hamiltonian of time-dependent harmonic oscillator, use Schrodinger equation. I mean, put this Hamiltonian in Schrodinger equation, and also assume that the state is Gaussian. Okay. Then we can calculate these correlation functions, different correlation functions, Mugano-Sasaki variable, and also there is a conjugate momentum. V is the conjugate momentum here. So you can calculate different correlation functions of Mugano-Sasaki variable and also the cross correlations. And what we observe, the power spectrum is basically this V square, which is the correlation function of expectation value of V square. That is the V is the Mugano-Sasaki variable. That is the power spectrum, and also it is multiplied by some background quantity. Okay. This is what we observe, this V square. Okay. So what I mean to say, from the Hamiltonian, quantizing this Muguno-Sasaki variable, you can calculate the v square expectation value. The expectation value is calculated with respect to the this wave function. So this is for the single field case. So similar calculations can be done for the multi-field case. So you have, suppose you have n number of fields in the during inflation. Okay, so you can construct a Hamiltonian from those n number of degrees of freedom, and assume the same. The state is Gaussian, and from that wave function you can calculate different correlation functions. But what we observe is simply the curvature perturbation. That's just 1 degrees of freedom. But there are n degrees of freedom here. So we observe only 1 degrees of freedom, but there are n-1 degrees of freedom that is inaccessible observationally. Okay. So these n-1 degrees of freedoms are basically, I mean, it's called isocurvature perturbations, and the curvature the perturbation which can be observed is called curvature perturbation. Okay. Others are isocurvature perturbations. So I think it's clear now. And okay, as I said, so this the Hamiltonian contains this the Hamiltonian associated with curvature perturbation and also n-1 isocurvature perturbation. And what we see is the curvature perturbation. So this system or this fact allows us to split the system into two. One is observationally accessible system, which is the Hamiltonian associated with the curvature perturbation, and the environment, which is the isocurvature perturbation. Okay, and there will be interaction between these two. Okay, and as I said, the sigma actually here denotes the curvature perturbation, and you can construct a covariance matrix associated with these sigma correlation functions. Interestingly, in single field models, the determinant of this covariance matrix is simply 1 by 4. Okay, and determinant of this covariance matrix, in the case of multi-field models, there are n degrees of freedom, and these n degrees of freedom are interacting each other. Then this determinant V is always greater than 1 by 4. Okay, so this is the main information, and using this correlation, this covariance, the determinant of covariance matrix, we can distinguish whether your model is single or multi-field model. Okay, or the power spectrum is coming from single field inflationary model or multi-field inflationary model. And also there are quantum measures associated with this covariance matrix. If the state is Gaussian, which is what I assumed, then the quantum measures such as decoherence, that is one of the quantum measure, and there are other quantum measures like purity, separability, and quantum discord, and recently people talk about complexity. So these are actually related to, if the state is Gaussian, then these are related to this determinant of covariance matrix. Okay, so decoherence is basically if the system, which is the sigma here, the curvature perturbation, interacting with the other fields. Okay, then you can construct this density matrix from this wave function. Then there will be some off diagonal elements because this system is interacting with the environment, and eventually or dynamically this off diagonal terms will be suppressed due to the interaction of curvature perturbation with isocurvature perturbation. So this is called decoherence. So this decoherence can be measured using entanglement entropy. Okay, so that is given by this expression. Again, as I said, this entanglement entropy is a function of some function of determinant V. V is the covariance matrix. So if the entanglement entropy is very large, associated with this sigma system, then we can say that the decoherence is very large in that system, which means eventually you can say that the system of this sigma is classicalized. Okay, because the quantum coherence associated with sigma is suppressed because of the interaction. I think this is clear. So I just put all this idea to some models. Here I specifically consider two field models. So we have curvature perturbation, we have isocurvature perturbation, and there's an interaction between these two. Okay. So also we find that this determinant V is actually proportional to the coupling parameter or the interaction strength between this curvature and isocurvature perturbation. Okay. Suppose a power spectrum is given. Okay. So we know that it is nearly scale invariant. So suppose the power spectrum is given. Okay. Suppose the power spectrum is given. We know that this power spectrum can be obtained from single and multi-field models. The same power spectrum. Okay. Exactly same. But as I said, quantum mechanically these are different. Okay. Because determinant V is different. That determinant V is basically what? It's some combinations of correlation functions associated with curvature perturbations. For different psi, if I introduce a different psi is basically the interaction strength. If I introduce different strength, but I have to make sure that it doesn't affect the shape of the power spectrum, you will see that this determinant V increases. Okay. Now we have two degrees of freedom. One is curvature, isocurvature. This is interacting with psi. So if I introduce psi at different times, then that will induce or that will enhance the determinant V. As I said, that will enhance the entanglement entropy in the system. Okay. So this is just a materializing or quantifying the determinant V in some model. Okay. And similarly, suppose the power spectrum is not scale invariant. It has some features that is also consistent with CMB observations. Okay, that also actually obtained from single and multi-field models. The exact power spectrum can be obtained from single and multi-field models. But again, these are different as we have seen. Okay. So in that case, suppose we assume the psi is introduced or active when the cosmological relevant scales are exiting the Hubble radius. Actually, this induces this kind of features, but the same features can be produced in the single field. And you know that determinant V is 1/4. But here you can see that in the case of two field models, it is not. So if we can observe determinant V, it is actually the some combinations of correlation functions. If you can observe that, we can distinguish or we can say that this power spectrum is coming from single field or multi-field models by examining the determinant V. But from the power spectrum, we cannot say anything. Okay. That's it. That's the summary. So, yeah, as I said, from a given power spectrum, we cannot distinguish whether this power spectrum is produced from single or multi-field, but you have to see the determinant V is actually some combinations of correlation functions. Okay. And also, actually, these correlation functions contains momentum correlation functions also. But curvature power spectrum is simply the curvature power spectrum. It doesn't contain any momentum correlation functions and cross correlation functions. And also the decoherence, this mechanism is also responsible for the classicality of the system, because we know that these fluctuations are produced as quantum, but we measure or observe the sky with some classical instruments or classical distribution functions. So somewhere in between, this fluctuation has to be converted to classical. So in this system, if the curvature perturbation is interacting with isocurvature perturbation, due to this decoherence mechanism, we can say that this curvature perturbation, the state associated with this curvature perturbation is classicalized due to the interaction. Okay. Yeah. Then, yeah, so there are other quantum measures such as purity, SSS separability, quantum discord. These are all related to determinant V if the system is Gaussian, but currently we are working on what happens if the system is not Gaussian. Okay, so that's it. Thank you.
Any questions or comments?
So this V, capital V, so this contains both position and momentum, right? So that is, if I
Yes, this one, right?
So, but typically when you talk about measurement, we don't measure two things.
Momentum.
So then how do you measure V?
V.
Yes.
V
contains, but it contains both position and momentum.
Oh, okay. Sorry, this V. Okay, okay.
Yes.
Yeah, it contains position and momentum. In principle, you can measure, but practically the problem is this momentum mode function, the mode function associated with this momentum operator decays. Okay, so we cannot see that in the CMB.
Yes.
But as I understand, if there is some observational probe where we can measure the time evolution of power spectrum, this is like galactic correlation functions. From there, you get the time dependence of our spectrum. There you can measure these V correlation, sorry, P correlation functions, then V. But from CMB, no, it's not possible.
Any other comments or questions?
So I'm also working other like inflationary and bouncing scenarios. So if you people are interested in these topics, let me know.
Okay. With that, we'll bounce to the next talk now. Thank you very much, Rathul, for very interesting talk.